particular, I'll concentrate on two volumetric effects. So I'll show how Perlin noise can be used to create convincingly looking fire, and how fluid dynamics calculations can be used to simulate smoke in real time. I will not give any code, despite the fact that this is a coding seminar. I will not show any chunks of code here. So my goal here today is to give you some ideas, some food for thought. And if you're really interested in implementation details, you can download these demos. These demos are actually included in our SDK, DX10 SDK, and you can go to developer.nvidia.com and actually download the SDK and see how they're implemented. But again, my goal is to inspire you for your next releases. So why this is cool? So as most of you know, I'm pretty sure that current approaches to rendering volumetric effects are rather limited. So you can either pre-compute animation loops into video textures and then play them back at runtime. But obviously this is not an option for demos because, well, due to storage constraints, and usually pre-computation takes too much space. And they're only valid for a limited set of viewing directions. So the effect will not look correctly if at runtime the camera direction changes, and if you look at it from a different point of view. So particle systems can also be used to simulate volumetric effects, but in order for particle systems to look good, you really need a huge number of particle systems, and that has some serious performance implications as well. So the techniques that I'm going to talk about are fully parameterized, in a sense that you can tweak any parameter, and basically you can blend this effect smoothly into the environment. So the effects are completely procedural in this sense. So the nice advantage, and I believe this is particularly important for demos, is that these effects, they take virtually no space. So we're not pre-computing anything. Everything is computed dynamically at runtime on the GPU. And these effects can also be pretty easily generalized to any other natural phenomena type of effects, such as water or clouds. So while we'll be talking primarily about fire and smoke, you can easily generalize it. So there has been a fair amount of research on implementing Perlin noise on GPUs efficiently. So at GDC 03, so as well, there has been some amount of research on implementing fluid dynamics in real time. So at GDC 03, Joe Stem came up with this paper called Real-Time Fluids for Games, and he showed how actually Fluid Solver can run in real time on the CPU. So he showed the CPU-based implementation, but then a bunch of people ported that approach to the GPU and showed something like 10x improvement in speed. So at the time, the simulator was basically 2D, so all the simulations were performed in 2 dimensions. And obviously, when moving to third dimension, the amount of computation increases quite a bit. So until recently, these techniques simply, they were not feasible from the performance standpoint, but now, since we have pretty powerful GPUs these days, you can actually implement them in real time on today's GPUs. And of course, modern graphics APIs such as DirectX 10, they provide some useful features which can be used to accelerate these effects even more, such as render to 3D texture, geometry shader, and stream out. So, by the way, before I proceed further, I'm going to show you how actually it looks like. Unfortunately, my laptop is not powerful enough to run this in real time, but believe me, this runs in real time, and you can download it and see it for yourself. So this is actually one of our SDK demos. It's called Perlin Fire. So you can tweak all kinds of parameters here to achieve different look and feel for the effect. You can just as well rotate camera freely. So it will show you in a moment. And the effect actually is fully volumetric, so it interacts with the objects. And it will look correctly from any viewing direction. So you can rotate it and look at it from different directions, and it will look correctly, unlike precomputed video loops. Okay. So first part of my presentation is dedicated to fire modeling. So first off, one thing to note here is that I'm not going to talk about physically accurate fire models because they are too expensive, and frankly, we do not care about physically correctness here. So we will use a technique called empirical modeling, and so our fire effect is going to be based completely on empirical modeling based on Perlin noise. So we're going to simulate turbulent flow using Perlin noise. So to give you some background on Perlin noise, so basically what it is, so it was introduced originally by Ken Perlin, so this is why it's called Perlin noise, in around 1983, so this is pretty much old thing. So Perlin noise is basically a signal which extends indefinitely in space and time. So it's space filling and time filling signal that gives an impression of randomness. So what this means is that it's band limited, so it's not completely noisy, it's not white noise, it's band limited, which means that most of the energy is concentrated in a limited range of frequencies. So it doesn't have a lot of high frequencies and doesn't have a lot of low frequencies, so it's band limited. It's isotropic, which means that whatever direction you go in space, the noise will appear pretty much the same. So it has the same appearance regardless of direction. It averages to zero, which is also a very important property. So on average, the energy it adds to another signal. So if you're summing up some other signal with this noise, then actually noise doesn't add any energy on average. So it averages to zero if you integrate it across the entire space-time. And it can be generalized to any dimension. So most of the examples that I'm going to show, they are based on 2 dimensions, simply because it's easier to show it that way. But it can easily be generalized to 3 dimensions, 4 dimensions, and so on. And this is actually what we're going to use for our fire effect. So this is actually how Perlin noise is constructed. And this is a classic approach to Perlin noise construction, the one that was described in the original Perlin's paper in 1983. So first we define a grid in our space. So if we're talking about 2 dimensions, that's going to be a rectilinear grid, so a grid of squares. And we mark each of our grid lines with an integer coordinate, so I and j. Then we define that at grid nodes, the green circles, our noise function has a value of 0. Then at each grid node, we define pseudo-random unit length vector. So the length is unit, but the directions are random. And basically, these vectors will define how our noise function changes, the direction of maximum change of our noise function. So it is a gradient vector of our noise function. So in the original Perlin implementation, these vectors are actually precomputed in a table. And this table is indexed with some hash functions of integer coordinates. So this precomputation is pretty much the only thing that you need to store in memory. And so the original implementation used like 256 to 156 vectors, so it's really small. So now, if you have a point in space, P, and you want to calculate a noise value at that point, the first thing you do is to construct these vectors which connect our points P to the neighboring grid nodes. And then you basically calculate dot products, pairwise dot products between these vectors. And then you simply need to interpolate between these dot products using some higher order function. So original implementation used simple Hermite curve, so the cubic curve, but we can use something even higher order to ensure smoothness of our noise function. So basically, we use fractional coordinates of our points P, U, and V to do that. So this is similar to standard bilinear interpolation, except that we're using this higher order function to instead of linear ramp. So if we do this for every point on our plane, or for every point in space, we'll get something similar to that picture. So it has some appearance of randomness, but it's not a white noise. So we have a controllable noise primitive. So like I mentioned, Perlin noise can be easily generalized to higher dimensions. So if we're going to 3 dimensions, then we'll have to compute 8 dot products, because there are 8 grid nodes for every cell. For 4 dimensions, there's going to be a grid of hypercubes. And correspondingly, there's going to be 16 grid nodes to calculate. So one unfortunate effect here is that the computation increases exponentially. So the higher you go, the higher dimension you go, the more computation you have to perform. So the amount of the interpolations and the amount of dot product evaluations increases significantly with space dimension. But the nice thing about it is that the storage is still negligible, so we do not really have to add anything more to that pre-computed vector table, except that our vectors are now have more dimensions, but that's not a big deal. So we'll see what we can do about computational complexity. But now I'm going to talk about a little bit how you actually use noise to create interestingly looking effects. So actually, noise by itself is not as interesting. So the key here is to use noise in various combinations to come up with interestingly looking materials and effects. So the common approach is to use this noise function to perturb values of some other functions, such as sine, or sum up several noise functions together and use that to modulate the result of some other function. So this is very common technique in film rendering, in offline rendering. So one useful primitive is called turbulence, which is basically a weighted sum of several noise octaves. So by octave here, we mean basically a noise function computed at different frequency and each having different amplitude. So usually for turbulence, the octaves, they relate to each other in so-called fractal relation, which means that every octave of the noise has twice as higher frequency and half of the amplitude of the previous octave. So we sum them up together, and the end result is something like you can see on the bottom of the screen, which can be used, for example, immediately as a cloud layer or a height map for your terrain or for ocean surface. So this is a useful modeling primitive. So now we'll see how we can use these primitives in order to model a 3-dimensional fire effect. So for any volumetric effect, the first thing we should do is to define a simple density volume in 3 dimensions. And then what we're going to do next is to use our noise primitive, our noise functions, to modulate this volume to add detail. And since we're computing everything on the fly, it is very easy to animate this effect. So nothing is pre-computed. You just change some parameters and it will animate automatically. So since we're talking about 3-dimensional space, we need 3 dimensions of our noise function to modulate the actual volume in space. And then if you want to modulate it with time, we need 1 more dimension. So that means that our noise primitive, our noise function, has to be of 4 coordinates. So that is 4-dimensional Perlin noise. So the 4th dimension represents time. So for fire in particular, what we can do is to exploit the symmetry of the effect. So instead of pre-computing entire 3-dimensional volume of space in order to represent the density, we can use simple 2-dimensional fire profile and then basically revolve it around vertical axis to come up with 3-dimensional fire volume. So the nice advantage of this approach is that artists still have some control over overall appearance of the fire. So despite the fact that the effect is completely procedural, artists can still draw these profiles and come up with different looks and feels for the fire effect. So now, once we have this 3-dimensional fire volume, we're going to modulate this fire volume with our turbulence function, which is based on Perlin noise. So you can see here we take our three-dimensional fire volume and then basically perturb it with our turbulence field, which has 4 dimensions. So we use 3 dimensions to perturb the spatial appearance, and the 4th dimensions to actually animate. So we're going to be dragging this turbulent field up in spatial dimension and in time as well to simulate intricate fire dynamics. So like I mentioned, the effect is very customizable. So you can, by changing the weights of the Perlin octaves, you can achieve all kinds of different look and feels for the fire effect. So basically the end result is a sum of these different fire octaves, and by tweaking these parameters, tweaking amplitudes and frequency relations, you can achieve all kinds of different fire effects. So it is customizable, and you can change it as you would like. So from performance perspective, unfortunately, using classical Perlin noise, just like it was defined originally, is extremely computationally expensive. So if you look at this table here, you can see that the amount of work grows exponentially with dimensions. So for 4 dimensions, you need to perform 15 interpolations, because we're dealing with a grid of hypercubes, and 16 dot product evaluations, which is quite a bit. So it is significant increase from 3 dimensions. So now you have to keep in mind that these numbers represent basically the amount of work you have to do for a single point in space for a single octave. So now if you consider that you actually need more octaves, so preferably you need to have something like 5 or maybe 10 octaves to create a detailed looking fire, then it really becomes not really feasible to evaluate in real time. So we have to do something about it. And fortunately, there is a way to address this issue. Actually, Perlin himself anticipated this problem with his original noise, and in 2001 he came up with another approach, which was called improved Perlin noise. So the core idea of the improvement is to use simplex grid instead of rectilinear grid. So what is a simplex grid? Basically, if we consider n-dimensional space, then a simplex is the most compact shape of n dimensions that can be tiled essentially in that space. So for a plane, a square is not a simplex because you can use triangle to tile the two-dimensional plane just as well. So for 3 dimensions, a simplex would be a tetrahedron, and similarly for 4 dimensions, that's going to be a 4-dimensional tetrahedron. So the key point here is that using simplex grids actually allows us to reduce the number of interpolations significantly. So our overall number of computation goes down, and basically now how you need to modify the original algorithm. So now, instead of having rectilinear grid in space, you have this simplex grid. Again, I'm showing this as a 2-dimensional example, but it can easily be extrapolated to higher dimensions. So now, in order to calculate which simplex we are in, we can actually do very simple transformation. And by doing non-uniform scaling, essentially skewing this grid across along the main diagonal, and transform this simplex grid into rectilinear grid, or vice versa, the other way around. So this allows us to very quickly estimate, evaluate which grid nodes we need to consider for evaluation. So the transformation is really simple. I'm not going to give you the exact math here. You can look at the paper. I'll give references later. The idea is really simple, is that you're skewing the grid and basically going from simplex grid to rectilinear grid in order to evaluate to find out which grid nodes to calculate. So the next improvement is that instead of using interpolations, linear interpolations, we're going to be calculating our final noise value a little bit differently. So at each grid node, we define so-called radial basis function, which looks like a Gaussian fall-off, essentially. So the intensity of the function, it has a value of 1 at 0, and then it falls off with distance. So now we basically take these radial basis functions and use them to attenuate the value of our dot products calculated at each grid node. And the result is simply a sum of these values. So again, it is much easier to evaluate it in this form than to perform actual linear interpolations. So let's see what we gained with using simplex grids. Again, if you consider if you compare classic noise to simplex noise, you can see that the amount of computation is significantly reduced. The amount of dot product evaluations, especially if you go to higher dimensional spaces. So while the advantage in two-dimensional space is not that great, in 3 dimensions, it's actually quite a bit more. And then in 4 dimensions, we're going from 16 dot product evaluations to only 5, which is really nice improvement. Which means that we can actually use simplex noise, simplex grids, to evaluate 4-dimensional Perlin noise, which is what we need. So now I'm going to talk about how to render our procedurally generated volume in real time. So the technique we're going to use to render this effect is called ray marshing, which means that we're going to traverse our volume and sample several times across the viewing ray, then integrate the results. So let's see how it works. So first off, we define a region of space where our effect is to be located. So we can use a simple bounding box or any other bounding primitive. And then we render front faces of our bounding box with a special pixel shader, which at each pixel transforms pixel coordinates, which are essentially our viewing ray coordinates, into a local frame of our fire effect. And then we perform sampling. So we take a number of samples along our viewing ray, performing calculations, turbulence calculations at every of those samples, and then basically summing up the results. And then we blend it back to the frame buffer. So now one problem with this approach is that if we are doing this sampling regularly, which means we're taking the samples at regular intervals, say within a loop, then we're going to get some not really nice looking bending artifacts. I'm not sure if you can see it, but basically it looks like a solid geometry. The fire effect essentially clips to solid geometry, which is not how it should look like. The workaround is actually very well known, is again in offline rendering, in film rendering. And what we need to do is to jitter our sample locations a bit, which is called jittered sampling. So what we're doing here is that we are specifically introducing a certain amount of noise into our effect to hide these artifacts caused by regular sampling. So we're trading off essentially bending with noise. And human visual system works in such a way that we can filter, we can deal with noise very well, because we're dealing with noise pretty much any time. So we can essentially the noisy effects, they appear more realistic to our eyes because we're trained to filter noise very well. So basically the idea is really simple. So instead of taking samples regularly at every pixel, now you have to basically shift your sample locations like this. So the amount of this shift is random at each pixel, and this is what gives you this noisy appearance. So now, of course, noise is not something that. So if your sampling frequency is really low, then noise becomes intolerable. So to work around that, you need to increase the sampling rate, which means that you need to take more samples at each pixel. But that, of course, means well, has some performance implications. But that's the trade-off you have. Questions? Everything is understood? No? Yeah.
So you sample along a line, but do you weigh these samples equally?
All samples are weighted equally.
Thank you.
Because you're essentially sampling the same density volume. There should be no preference in sampling. Yes?
When you said before that you're modulating the fire volume with the Perlin noise, how exactly is that done?
It's basically you add, so you calculate your turbulence volume, right, the turbulence function, and then you use this value, you add this value to a texture coordinate to look up into the two-dimensional fire profile.
Oh, okay, yeah, I see.
So you shift your texture coordinate based on Perlin noise.
All right, thanks.
Okay. Any more questions?
One question.
Sure.
Do you actually stop the rain a certain distance if you hit, for example, like already the maximum?
That's a good question. So, for example, if you rendered your solid geometry, your opaque objects into Z buffer, then you can actually sample the Z buffer to find out whether you need to stop sampling. So yes, we are doing that in the demo. So if, for example, you have solid objects within the fire effect, you will not be sampling through them. You need to stop at solid geometry. And you can find out where to stop by sampling the Z buffer.
You talked about earlier about that the flames actually move around your object, but as far as I see, you're actually calculating in the object, but you don't draw them.
So they clip to solid geometry, but for fire, it is not as objectionable. So the next effect I'm going to talk about actually interacts properly with solid geometry. So, we're talking about two different effects here. So one is based on empirical modeling, which is fire. So it is based completely on noise. It doesn't have any physical correctness to it. It is completely ad hoc. It is completely empirical. But it looks nice, right? The next effect is smoke, which is actually based on physically correct computations. It tries to approximate the proper fluid flow in space. And if you have solid geometry in that volume, it will properly interact with the smoke. So I'll show you how it works in the next section of my present. Okay? Okay. So the second part of my presentation is going to talk about smoke rendering. So I'll overview the overall process a bit, then I'll give you some background on fluid simulations, and then I'll show how to deal with arbitrary boundaries. So that was the question, how to deal with objects within the smoke effect and how they can actually interact with the volumetric effect. So rendering for these effects are actually pretty similar. So first we need to render all of our opaque solid geometry into a frame buffer. So we have our frame buffer, and then again we define a region of space where we want to place our smoke effect. So we can define it using a bounding box. Then we discretize the space into grids and perform simulations, fluid dynamic simulations on that grid, in that discretized representation of space. Then we do rate marching, similarly like we did for fire, except that in this case we actually have our volume, simulation volume, stored in memory. It is computed procedurally, but we store this as a 3D texture in memory. So I'll show you how it works in a moment. And then we composite the results back onto the frame buffer. So this is all very similar to what we have seen with fire. So what is fluid simulation? So a fluid, it can be, for example, an air in this room or a water in a river. It can be defined by a number of fields in space. So we can talk about density field, velocity field, or pressure field. And there are mathematical equations called Navier-Stokes equations that define how fluids, how these fields, which define fluid, evolve in space and time. So these equations are actually physically accurate. So they try to approximate what is actually going on in the physical world. So the key points that they impose basically mass conservation and momentum conservation on our fluid. So we don't have sinks in our simulation. So basically, since we're dealing with digital computers, we need to discretize our space into grid and then solve this differential equation. So Navier-Stokes are differential equations on this grid to evaluate the values of our fields at new time step. So basically, this is how it works. So first, we initialize our grids, which are to represent our fields. So we have a density field, density grid. We have velocity field and pressure field. And now at each time step, we need to evolve these fields using Navier-Stokes math to evaluate the value of those grids at new time step. So at every time step, we go through several sub-steps. So the first sub-step is called advect, which means that we're using our velocity field to move the density, to propagate the density along the velocity to create a new density field. Then we can add density to our simulation, so we can inject smoke into our simulation, inject fluid. We can add velocity, so when we inject something, we can give it initial velocity. And then the last step of the simulation, the last sub-step, is called project, which basically means that we need to ensure that our velocity field is divergent free and the mass is being conserved. We're also imposing our boundary conditions in this sub-step, which means that we do not want our fluid to flow into solid objects, and we want our animated solid objects to interact with the fluid. So we do this for a number of time steps, and then eventually we arrive at a new set of grid points. So now I'll go into a little bit more detail on the advection step. So basically we have our density and velocity textures, density and velocity grids at time step t, and now we need to calculate our density grid at time step t+1. So what we're going to do is, for every cell in our final grid, we're going to take the corresponding velocity value and track back its velocity into the density grid and sample from there. So, and then we can take that density at that point. So if it falls in between grid nodes, then we use simple interpolation to find out where to sample from. And replace, basically output this density as a new density value. So since we're doing it on the GPU, of course, we store our velocity, density, pressure, texture fields in textures. They're going to be two-dimensional textures for two-dimensional space, and similarly three-dimensional for three-dimensional space. And then when we simulate one sub-step for entire grid, basically we're going to render full-screen quads, screen-line quads, basically forcing the pixel shader to run at every grid cell. So we're doing all of our computation in pixel shader. So this is all pretty obvious and very well known for people who know what GPU simulation is. So this is basically how advection step works on the GPU. We use texture fetch to sample from a quad texture and then output our final value to a new render target for time step t+1. So since we're dealing with three-dimensional space, our textures are have 3 dimensions. So we're gonna be dealing with volume textures, and at this stage, actually, we need to be able to render to 3-dimensional texture, and this is something that you cannot do in DirectX 9. So this is why we need DirectX 10, new functionality of DirectX 10, which actually allows you to render to slices of 3D textures. And you can do it in one pass, because you can essentially use a geometry shader to direct which slice to render to. So we're using new functionality of DirectX 10 to render to 3D textures here. So now, obviously, like somebody mentioned, we need to make sure that the effect, the fluid, interacts properly with obstacles, with our solid geometry, because it will have serious implications of the realism of our effect. So as you can see on the left picture, we're simply simulating smoke without having it interacting with the environment, which doesn't look as nice. So ideally, we would like our objects to actually affect the movement of the fluid, affect the movement of the smoke. So how we're going to do that? So first off, we need to find a way to represent our solid geometry, to somehow communicate this information to our simulation. So one approach is to use implicit shapes. So we can define some shapes procedurally, such as use spheres or cylinders to approximate the overall shape of our solid geometry. Or we can actually voxelize objects, which means that we can take our mesh, triangular mesh, and then find out, basically discretize it, and then find out which cells are occupied, which cells are within the geometry, within the object, and which cells are outside. So we need to come up with some sampled representation of our geometry. So in order to voxelize, we'll of course need a three-dimensional texture, a volume texture. So we take our objects and then basically slice by slice we can voxelize it by rendering to 3D textures. So if we're dealing with static objects, we can just as well voxelize it once for simulation and then reuse the results multiple times. If we're dealing with dynamic objects, such as this one, which actually flaps its wings in the demo, we need to voxelize it per frame. So we need to perform the voxelization at every frame, which can be quite expensive. So now, in order for the fluid to interact with our obstacles, we need to modify our fluid simulation a bit, which means that we need to enforce two basic conditions, and these conditions are called boundary conditions. So one of them is that fluid obviously should not enter obstacle cells, that is, cells which are occupied by our geometry. And if obstacles are moving, then basically they should impact the movement of our field, of our fluid. So it has to modify the velocity of the fluid somehow. So in order to enforce these conditions, after the advection steps, in the projection step, we basically need to satisfy these conditions. So satisfying conditions for density are actually pretty simple. So basically we need to make sure that we do not allow density to be present within the obstacles. So we need to remove density from those cells. We also need to make sure that certain conditions are satisfied for our pressure field, which means that for two adjacent cells, if there is a cell occupied by an obstacle, then we need to make sure that between these two cells, between the free cell and the occupied cell, the pressure gradient is 0. So it's called Neumann boundary conditions. And similarly for velocity, we need to make sure that the velocity, the normal component of the velocity of the occupied cell is equal to normal component of the fluid in the cell next to it. So I'll show you how it looks like. So if you have an occupied cell, which is to the left, so let's say this cell contains some objects which has this velocity illustrated by an arrow. We can decompose this velocity into two components. One component is basically along the normal direction, and another component is in orthogonal direction. And then if we have a fluid in the cell adjacent to this one, which has its own velocity, we can similarly decompose it into two components. And then basically we need to make sure that the normal component of our obstacle velocity is equal to the normal component of our fluid velocity. So we need to modify this arrow here. And recalculate new velocity for our fluid, which is going to look like this. So this is all pretty straightforward, actually. So now I'm going to talk a bit about how to actually perform the voxelization step. So the result that we are looking for is these two textures. So we need an obstacle texture, which tells us which cells are actually occupied by our geometry, and then we need another texture which represents velocity for